Okay, awesome. So welcome everybody to the second day of the Data Science Week. Now we have the great pleasure to have here Professor Ching-Yao Lai. She is a professor in geophysics and a member of the Institute for Computational and Mathematical Engineering at Stanford. She's also an executive committee member in the topical group on the physics of climate from the APS. From 2021 to 2023, she received many honors and awards. A Sloan Fellowship, which is still holding. She had the Research Scholar Award from Google, Lamont for Postdoctoral Fellowship from Columbia. She has been a PhD student at Princeton in Mechanical Aerospace Engineering, and she was a Bachelor in Physics from the National Taiwan University. She works in many problems in geophysics. From my perspective, she is an applied mathematician and machine learning researcher with interest in geophysical sciences. Today she's going to talk to us about machine precision neural network for multiscale flows. So thanks a lot for the opportunity to hear about your research.
Okay. Thank you very much, Alessandro. And first of all, I just want to thank the organizers for the invitation and the kind introduction. So if the slides are looking good, then I will go ahead. And okay. All right. So can you see my laser pointer here?
Yes.
Okay, great. And yeah, so I this is the Data Science Week, right? And today I'm excited to tell you about some of the recent work my group have been developing, trying to enhance the representation accuracy of neural networks. And I hope I can convince you that it is problematic that a vanilla neural network often suffers to represent multiscale data, which motivate our group to develop highly accurate neural networks. And this work that I will talk about today was also published earlier this year in Journal of Computational Physics. So just a little bit of motivation. There, as you know, there has been an emergent trend of research using machine learning models, in particular neural networks, to emulate numerical simulations to substantially reduce its computational cost. Success stories include the recent bloom of the machine learning-based weather forecast model. So classical weather prediction model is made by numerical solving a couple of PDE partial differential equation that describe the evolution of the atmospheric states, and that's denoted by Z. In a machine learning emulator, a physics-free machine learning model is used to approximate the dynamics, and that's denoted by F here, and it's described the time derivative of the states. So what a machine learning model is doing is that it will take the states from the previous time as input and then output the state in the next time as output. Once you train a machine learning model to learn this mapping between previous and next time step, you can use this to make time stepping predictions. So the ML model will take the previous time step as the input, make the next time step prediction, and then take the next time step prediction as the input, and then make the prediction in the next time step, and so on. So it has been shown by various papers that this approach is really successful. So DeepMind, for example, they showed that after training on the EVER5 weather reanalysis data, they can train a neural network to make a weather prediction that is comparable to the state-of-the-art physics-based weather prediction model. And the downside of this type of approach is that it takes a long time to train, but the nice thing about it is that once it's trained, it takes almost no computational cost to make prediction compared to the classical numerical simulation. So here is an example of the global wind field made by such a machine learning-based weather prediction model. And if we look at the wind field pattern and compare that with the numerical simulation that it is trained on, you can see, so one of these map is from numerical simulation, one of these is from machine learning based model. I usually ask people to guess which one is ML based, but here I will just directly show you the which one is which. So the left side is the machine learning based model, and the right side is the classical numerical weather for prediction. So you can see, first of all, these two are almost indistinguishable. But second, you can see that the ML model, while it captured the large-scale wind field pretty well, it's really missing some of the fine-scale detail that's present in the numerical simulation. And this is because the numerical simulation is actually resolving the partial differential equations that give rise to this fine-scale physics that is missing in the machine learning-based model. So you can further quantify this effect by looking at the spectrum of the wind field. So the plot below the horizontal axis is the Fourier transform of the wind field, the wave number. The vertical axis is the density. And the black line is from the traditional numerical simulation. The colored lines are from the spectrum from the machine learning based model. So you can see that a lot of these ML model that capture the spectrum as small wave number, meaning that it capture the large scale feature pretty well. However, this ML model tend to miscapture the fine scale details, and you can see that is reflected in this deviation from the true spectrum at larger wave number, which is corresponding to smaller, finer scale patterns. And this is even worse if you look at the prediction at longer time horizon, right? At day 10, some of the ML model even fail to capture the larger scale pattern.
So just to make sure I'm understanding correctly, oh wait, there is some.
Yeah, I can hear you.
The question is, so it's missing the high frequency component. So the machine learning algorithm is missing the high frequency component. Am I correct?
That's right. It's missing the small scale details.
Okay. Okay, good. So for example, in the oceans, some of the currents are missing some wiggling around.
Yeah, like that, something like that. And this is a pretty common observation that you will see in a lot of the neural network based emulation. So I will show in the slide the cause of this effect. So this type of missing fine scale feature is also related called the spectral bias of neural network. So I don't know how many people in the audience are familiar with this concept, but the spectral bias of the neural network, it refers to neural networks' tendency to prioritize fitting functions with a certain frequency range. So I really like this paper, 2019 paper, because it's a really simple demonstration of the spectral bias of neural network. You can see in this paper, the blue line is the target function that we're trying to fit. The green line is the neural network prediction. And you can see that the neural network fits the large scale variation immediately, but it takes much longer iterations to capture the scale high frequency details. So this is generally not a good news. It's actually pretty bad news for us because problems in earth sciences, in climate, or more broadly in physical sciences often exhibit multi-scale features. So neural network, we choose to use neural network because its property as a universal function approximator. However, in reality, in practice, neural network often fail to capture the fine scale details due to its spectral bias. And there are actually many solutions that has been proposed. One of the popular solution is called the Fourier feature. So the top image here is just simply using a multi-layer perceptron to fit an image, and you can see exactly what the problem we described before. It's capturing the large scale feature, but then it's kind of blurry, right? It's missing all the fine scale details. So if you use the Fourier feature, you simply, before passing information from the input to the hidden layers, you add the so-called Fourier features, which is composed of a list of sine and cosines with some prescribed wave number. And the idea of this, the intuition of this is that you're giving some hints to the neural network that there's a spectrum of the frequencies that are relevant to describe the data. So the lower row here is the image after imposing this Fourier feature, and then you can see that it now is capable of capturing these fine scale details in the image. Okay, so in today's talk, I want to talk about two major questions to address. One is what are other strategies we can apply to tackle the spectral bias of neural networks. And additionally, out of curiosity, we're also interested in, if neural network is truly a universal function approximator, what's the limit to its accuracy? How can we make it as accurate as possible? So this is the outline for today, the talk. First of all, I want to tell you about a algorithm our group developed to boost neural networks approximation accuracy down to machine precision for multi-scale data. And I'll talk about two applications. I suspect I probably only have time to talk about one of them, but these applications are related to use of neural network to solve some inverse problem. And this inverse problem exhibit multi-scale feature, therefore it's quite important to be able to tackle the spectral bias. Okay, so let's get started. And I thought about whether to briefly introduce neural network. I thought just in case, here's a brief introduction of the simple multi-layer perceptron. When we use a neural network, we are really trying to use it as a function approximator, right? Here, this neural network is basically a function of output u as a function of input x. And as you know that when we pass down the information, we simply have some weight that's training parameter that's multiplied by the input before passing the information into the input layers. And after that, we impose a nonlinearity that's called the activation function. So this expression is the output of a neuron in the first hidden layer. And you can choose your favorite activation function. I'll talk more about which one we use. So you can basically do this for all the neurons in your first layer, and you can sum up the output together after multiplying the output with the corresponding weights that's connecting the output in the first layer to the second layer. And then this expression is the output of a neuron in the second layer after imposing the activation function. So the operation is really straightforward, and then all you do is to just repeat this for all the neurons throughout the multi-layer perceptron, and you can write down a nasty form of the output of the neural network as an analytical expression as the input. So all that matters here is really that there are lots of weights and biases, and these are free parameters in this expression that is to be determined throughout the optimization process. So it has been shown that this type of architecture can be used as a universal function approximator. And in fact, if you reduce the neural network down to one single layer, and then if you use signs as an activation function, then the analytical expression of the neural network is really close to a Fourier series. So here the weights that's connecting the input to the hidden layer represent the frequencies in your Fourier mode, and the weights connecting the hidden layer to the output represent the amplitude of the Fourier modes. So you can then think about questions like, if you're trying to fit a periodic function, maybe it's better to use a sinusoidal activation function because that's where Fourier series works pretty well. But if you have a Gaussian-like or like a delta function, then you know that Fourier series is a terrible way of describing the signal, because then you will need infinite number of Fourier mode, right? So that's a really inefficient use of your neurons. Therefore, for this type of signal, you want to consider using hyperbolic tangent instead of sinusoidal or cosine activation function. So as you know, this type of neural network is really good for fitting curves. So what it does is, you have some data points. The neural network, again, it output u as a function of x in this case. And then when you train a neural network, you are essentially trying to find the weight and biases that parameterize the neural network such that it minimizes the cost function that characterize the distance between the neural network prediction and the discrete data points. So, okay, so that's a brief intro. Here, just to show that the expressiveness of neural networks. So this here, my postdoc Yangji, he tried to use a very simple vanilla neural network to fit an analytical 1D function. So here the y-axis is the output of the neural network, the x-axis is the input of the neural network, and then we have a made up analytical function, that's the blue line. So the neural network can do a good job fitting it, not surprisingly. If you look at the loss function quantifies the difference between the neural network and the analytical ground truth function. So it decays and then converges to an loss that's about 10 to the minus 5. So this is pretty good, I think, in most applications, but we were wondering why is the question is why is the error not lower, right? If the neural network is truly a universal function approximator, why can we get the error even smaller? What fundamentally limits this error bound? So here, no matter we try to increase the neural network width, neural network depth, that's usually the first thing you can think about doing, making more free parameters. We train for a longer time, but none of those options can push the error further down. So here we propose a multi-stage training scheme that use a second neural network to efficiently learn to correct for the error from the first neural network. And we showed that this multi-stage neural network can achieve much better precision, as you can see by this black line. So the precision is lower with less number of total parameter compared to this single network, and therefore the computational cost is actually lower for the multi-stage neural network compared to the single regular neural network. And before I talk about the details of this multi-stage neural network, I just want to draw your attention to this really elegant explanation of the spectral bias of the neural network. So again, we showed earlier, this is an expression that you can write down for a single hidden layer neural network, where the x is the input, u is the output, and this w are b are the training parameters of a neural network. So the mean square error here is just the mean square distance between the neural network prediction and the ground truth function. And here we're going to write everything in the Fourier domain. So the hat of u denote the Fourier transform of the neural network prediction. And as you know, when we do the optimization using gradient descent, we are trying to update the cost function based on the gradient of the cost function with respect to the neural network weights and bias, right? So we are trying to calculate this gradient here. And it can be shown that this gradient can be written, it decay exponentially with k, which is the frequency or wave number of the neural network prediction. So this is important because this shows that for this gradient will become really, really small for large k, large frequency, meaning that it will take really, really long number of iterations to learn high frequency functions. And this is a simple explanation for the spectral bias. So again, here we have this really bad exponential decay with increasing frequency or increasing k. To mitigate this problem, one simple trick you can do is to rescale the weights in your neural network. Because if you look at this decay rate, the k over w, the frequency is rescaled by the weights. W is the weight of the neural network. So if we make the weight of the neural network proportionally, we make it increasing with k, which is a function, the target frequency we want to fit, then you can really make this gradient large again and then reactivate the learning of high frequency function. So the simple implementation is the following. This is our implementation. This weight is simply this coefficient, the weight connecting the input to the first hidden layer. And we just add a scaling factor kappa. And you can, if you have large kappa, then you can capture high frequency functions. Okay, so that was about how do you deal with high frequency functions. Now we have another independent issue to overcome. When you train a neural network, when the training error is small, the learning becomes very slow. So here the main idea here's the main idea of multi-stage neural network. And we write the neural network approximate function as a superposition of the leading order approximation U0 and the higher order error terms like U1, U2, etc. So in this superposition, the epsilon 1 is a small number compared to 1, and epsilon 2 is a much smaller constant compared to epsilon 1, etc. So here U0, U1, U2 are neural networks from different stages. One important thing is that U0 is about, the output of U0 is about orders of magnitude 1. The output of U1 is also around orders of magnitude 1. So it's actually very easy to train these individual neural networks. So the key idea here is that although one single neural network is quite difficult to get it to capture both the leading order signal as well as the high order errors, we can use a superposition of neural networks to capture all the higher order errors and that's much easier compared to having one single neural network to capture all the details. And I should add that there are many related work with similar flavors used for different applications that's listed in here. Okay, so let's take a look at how this work, some numerical experiments. Here again, another simple 1D function. U is the output, X is the input. The blue line is the ground truth function. The dashed red line is the first one single neural network. So after one single neural network, you can plot the error function. So this is the distance between the ground truth and the neural network prediction as a function of the input X. And as I said earlier, we can use a second neural network to fit and correct for the error of the first neural network. And now this second row here is the error from the second neural network. And now it has a much smaller amplitude, so about 10 to the minus 8. So one thing to note that is, if you look at the error of the second neural network, it also has higher frequency. So here the right plot is a Fourier transform of the error of the second network. And you can keep doing the same thing, use a third neural network to learn the second neural network. And now this error of the third neural network now reaching 10 to the minus 11 and even higher frequency. And you can just keep doing this until it's reached the desired frequency that you wish. So if you look at the total error as a function of number of iterations, the convergence rate is much better compared to using one single neural network. And here is an interesting observation we found. So the scaling law of this neural network is quite good. Here, as you see before, when we use subsequent neural network to increase the expressiveness of the multi-stage neural network, the resulting error has smaller amplitude in each stages, but it also has higher frequencies. So if you look at the amplitude of the error versus the frequency in subsequent stages, it obeys a 1/6 power law scaling. And we found that this scaling is actually quite universal across various different target function that we try to fit, and also a range of neural network size and width. And so that was just for 1D data, right? And then here I want to show that you can actually use this to fit higher dimensional data. So here my student Jenkin, she write a spectral solver to solve this 2D incompressible Navier-Stokes equation in a vorticity form. So here is the numerical simulation she created. There's no neural network here yet. This is just a classical numerical simulation. And so this is the vorticity that evolve with time and space. And this is a good example of multi-scale data because if you look at the spectrum of its energy, it spans over 2 orders of magnitude. The x-axis is the wave number here. Okay, so the goal here is really simple. We just want to see whether neural networks, whether we can use multi-stage neural network to tackle the spectral bias when fitting a flow field like this. So here we take a snapshot. This is the from the simulation, the target function from the fluid solver. This is a neural network approximation. So after one neural network, you can see that these two are almost indistinguishable. But if you look at the error, so subtracting the neural network from the target function, you can look at the amplitude of the error. And then you can look at the loss convergence. And then the energy spectrum is really where you see the issues. So the black line is the true energy spectrum from the numerical simulation. The blue line is the spectrum from the neural network. So you can see it's capturing the large scale flow field quite well, but really missing the fine scale details in the data. And then you can see that in this deviation from the true spectrum at larger wave numbers and larger frequencies. So if you look at the error of this first neural network and then look at it in the Fourier space, you can see that it has a particular characteristic error frequency associated with error. And this is kind of what we saw earlier. So now we can use a second stage neural network to capture the error from the first stage. Now the second stage error has a much smaller amplitude, so 10 to the minus 7. And if you look at the spectrum of the second network, now it captures a broader range of frequency, but still miss the highest frequency details. And you can see now the error of the second neural network has a larger dominant frequency. And not surprisingly, if you just keep applying this strategy, you can essentially push the error down to close to machine precision of the double floating point. And in that case, the energy spectrum is perfectly captured by the multi-stage neural networks. So just to sum up, here we show that multi-stage can tackle the spectral bias. This is the energy spectrum. The gray is the target spectrum. The red curve is what you usually would get if you use a regular neural network. You miss the large scale, fine scale physics because of the spectral bias. If you use the multi-stage neural network, you can essentially tackle the spectral bias. And if we look at the loss convergence, you can see that compared to training one single neural network, now this red line is one single neural network with same number of total parameters compared to the multi-stage neural network. But the error converges over time, over iterations. However, if we use the multi-stage neural network, you can effectively keep increasing the expressiveness of the neural network. And eventually, this can achieve unprecedented accuracy down to machine precision of double precision floating point. And so most of the details are in this paper in Journal of Computational Physics, but we also have a more recent ICML workshop paper in arXiv. Okay, so this is just a summary for, you can really, for regression problem, you can really use a multi-stage scheme to correct for the errors using a second neural network. And I want to emphasize that actually all this procedure can be automated. Like the error of your previous network is known once you train a previous network, and then the corresponding frequency of your error is also known once you train a new network. So you have all the information that's needed to design a multi-stage neural network.
I have a question about that. So when you you run the first network, then you get the error. Do you start a new network from scratch, or do you use information from the first network?
That's a really good question. We use the information from the previous network because after we train the first network, we freeze the first network. So we remember all the parameters. So the parameters from the first network is frozen. And when we train the second network, we're just learning the residues. So we are learning new parameters, but we are still we are not retraining the first neural network from scratch. So
the reason, go ahead.
Go ahead. Yeah.
The reason for which I was asking is this one. Usually, when you do this sort of expansion in epsilon, okay, then what happens is that you end up having a sequence of equations which you have a linearized operator applied to whatever perturbation equal to a source term. Now, the source term comes from the nonlinearity, but when you iterate this method, basically the solution at step n+1 depends on the solution at step n. So there is some sort of natural algorithmic structure there. And so that's why I asked if you take advantage of that, and it looks like you do.
That's right. That's right. I think you might be interested in. I actually didn't put that in this talk, but I was talking about just fitting functions. So we know there's no equations here. It's just fitting function. But we actually apply the same idea to solving PDEs, and
Right.
in there, it's actually really really important to figure out what's the PDE that the second neural network is trying to solve, and that's definitely dependent on the solution from the first neural network.
Right.
So that's also in this paper, and we're trying to write a more thorough paper on that topic. But definitely, the previous network is we need to remember the information. So some people also ask whether we train all the four network altogether. The answer is no, because pretty much once the first network is trained, if you keep training for longer, you're just wasting computational time. Like basically, the first neural network has exhausted its expressiveness already by capturing the first order signal. So that's why we stopped training the first network when we train the second network. But we definitely remember we're using the information from the first network when training the second one.
I think there's another question from the audience.
Yeah.
Neha, I think.
Yeah. Thanks for sharing this content. It's really good. I had a question. This might sound really basic. Like, how are we handling the bias which is carried from the previous network to the next network? Because there must be some biasness added in the output data. So when the number of layers are huge, I mean, will it not keep on adding the bias at every layer and make the result less perfect than compared to what we expect?
So can you clarify what do you mean by bias of the first network? So here is the
So
yeah.
yeah, I mean, I didn't get the in-depth clarity about the graphs, but what I have doubt is what the biasness in the output, like the result which we are getting from the first input layer will be getting added to the second as input, right? I mean, that biasness will get added, right, at every layer as we proceed further.
Right. So I don't know what you mean by bias, but essentially
Mhm.
we're trying to correct for the bias of the first network by training a second network.
Yeah.
So I don't know if I use the word residue, like error,
Okay. Yeah.
to
Right.
so to me, the bias, maybe you have a different definition of bias, but the bias of the first neural network is the spectral is in the spectral domain. Like each
Mhm.
network is prioritized to characterize frequency of certain frequency range. So that is the bias. And in order to correct for that bias, I think it's extremely difficult to force one single neural network to do
Mhm.
that. It's much easier to create a second network. For example, you look at the bias of this second network is such a high frequency that you just cannot capture anymore.
Yeah.
Right? So, but it's easier to get a third network that's using the strategy I talked about earlier. You can rescale the weight, so the subsequent network is always optimized to fit frequency of different range based on the frequency observed from the error in the previous network.
Okay, so you mean the increasing frequency is reducing that error, right?
That's right. Like you can see from actually this is a very good plot. Like it
Mm-hmm.
the first row is the error from the first network. The second row is the error from the second network, and it's the second network can capture this error from the first. The second network can capture this first network mostly because we optimized the second network the weights of the second neural network to capture higher frequency. So that's why the second network can correct the bias of the first network.
Okay. So it's getting corrected at every time in the
That's
next
right.
loop.
That's
Okay,
right.
okay.
And thanks for the
Then
question because I didn't make this very clear in the talk, but it's such an
yeah.
essential step. I think if you want machine precision, you really need to care about the correcting the bias of the frequency
Mhm.
at subsequent neural networks.
And just last thing, just for clarification, I'm saying that you said that we need to change the weight values for correcting that bias, right?
That's right.
So how do
That's
you
right.
decide what is the perfect weight value for that? Like, do you experiment?
That's also a great question. So this is how we did it. You can simply just add. This is a quick and dirty way. You can just add a constant in front of your weight to
Mhm.
effectively increase the weight. Or we can think about that as a way of rescaling the input. So you're
Oh,
stretching the axis such that your high frequency become low frequency now. But so your question is, how do we determine this kappa, right? Like, how do we determine how much,
mhm.
how to rescale the weight? It is really essentially all in the result of the previous network. So we look at the result of the previous network. So this is the error of the previous network, and our goal is to train a second network to capture this error. You need to know the dominant frequency of this error. So we look at the error in the Fourier space, and then look at the dominant frequency. So this is the Fourier transform of the error that give you the dominant frequency of the error is what we use to rescale the weight of the network. For example, now after the second network, we have a really high frequency error, and you can see that. Apologize for the small fonts. The Fourier transform of the second stage error now has a dominant frequency that's about 29. So it's
Yeah.
an orders of magnitude larger than the typical frequency of error in the previous network. So we need to use we use this number 29 to as the kappa for as the weighting factor for the next subsequent neural network.
Yeah, and the W values are already predefined before training the model.
So the W is is we use some the Xavier initialization scheme.
Okay.
So that's just a typical initialization scheme. All we did is to have this kappa. So I'll say to train subsequent stage, you need two things. You need the error of the previous stage, that which you do have, and then you need to know the dominant frequency of that, which it can be known by doing a Fourier transform. We're
Yeah.
trying to write a package to wrap this all together so that you don't have to do it by yourself. So the user don't have to do it by themselves. But
Great, great. Thanks a lot for answering that. Wonderful.
yeah, so I guess we have. I think it's great to have time for questions and discussions. I think I'll just briefly mention the ideas behind the two applications. So I have my group have substantial interest of using neural network to solve inverse problems. A lot of these inverse problems are constrained by partial differential equations. So also back to the question to the previous question, I've also spent a lot of time to think about how to develop really, really accurate neural network based solutions when it comes to PDEs. And here are two examples. They're quite different in flavor. The first one is to show that you can essentially use this multi-scale neural network to capture geophysical data in the real world, and a lot of them are actually multi-scaled. So just naively fitting one neural network we often suffered from the spectral bias, and that's why that's how the multi-scale neural network relates to this project. And the motivation of this is to really, we know that to predict the ice sheet plays an important role of the climate systems, right? It contribute to the global rising sea levels. So there's substantial interest in making a prediction of ice sheet and how much it will lose its mass in the future climate. However, one limitation of this problem is that we do not, the prediction of this relies on the viscosity structure of ice sheet, which we cannot directly measure. So that's why we need to solve the inverse problem. And I'll just skip ahead. So the inverse problem we are trying to solve is the following. Here we have a set of partial differential equation that describe the dynamics of ice flow. And this equation involves many parameters that can be directly observed. We actually have very good ice sheet wide observation of velocity and thickness. And the only thing we cannot observe in this governing equation is the viscosity. And this is what we are trying to solve using the neural network. So here, the neural network is doing something that's both fitting the observations and as well as fitting the governing equations. So in the neural network, we are using this neural network to create a continuous representation of the velocity fields and the thickness field. And after the neural network fits the observational data, we impose a governing equation. We substitute it into the governing equations to see how we satisfy the physics. And this is the major result of this inversion. So this is the inferred the neural network prediction of a viscosity field using the real observations from real satellite observations of velocity and thickness. And so as we do not have any observations of viscosity field. It's just impossible to measure it in a real field. So the fact that we can predict this is really because we have governing equations in a cost function, and you can quantify the accuracy of these by substitute that back into the governing equation, and then you can look at the equation residue. It will be 0 if the viscosity is 100% correct. And here we show that the residue is about 2 orders of magnitude smaller than the terms in the equation. And just to point out, if you're interested in any like this kind of large scale geophysical problem or I don't know biomedical data, very often one single network is insufficient. That's what we suffer from. And here we did use a multi-stage neural network to tackle the spectral bias, so you can capture the details that are relevant to the physics of the problem. And for the rest of the maybe 2 more minutes, I will talk about the second example. So the previous example, we talked about a multi-scale inverse problem, right? But we actually didn't have to have a very, very accurate representation. So when we developed the multi-stage neural network, we were very curious if there's any applications that requires high precision neural network. And it turns out that it can actually be used to find PDE solutions that are otherwise difficult to find. For example, I'll talk about this in 2 minutes. We try to use this machine precision neural network to find singularities in fluid dynamics. And this is motivated by the Millennium Prize problem. So we know that the fluid dynamics can be widely described by the Navier-Stokes equation. This is my favorite equation in the world because it's really universal. However, there's some fundamental questions related to the equation, such as whether the Navier-Stokes equation always exists a unique and smooth solutions at any times. And one pathway that many people have tried to tackle is to find a counterexample. So if you can find a solution to the equation that will blow up at a finite time, that would be a counterexample. And here we want to see if we can use this highly precise neural network to help find a blowout solution. And our work, I should mention, Navier-Stokes equation is really, really difficult. So for the paper that I will talk about, it's really focused on the Euler's equation. And I'll just directly jump to the result. So you can write down a set of equations that you are trying to solve. So here is the self-similar Euler's equation. And I should add that this network, one thing I really like about this type of solver is that it's really easy to adapt to different problems. We are literally just taking the same neural network that we use for the ice sheet viscosity inversion to this problem by just changing the equation. And so here we have the set of equation we are trying to solve, and then we are trying to find the solution that satisfies this set of equations, but also exhibit singularity. I'll just directly she mentioned that if you're interested, a lot of the detail is also explained very well in this Quantum Magazine article, and the main result is explained in this paper in PRO that was published last year. But we showed that after training, as your loss function converges over time, you can see that these are the 5 different set of solution profiles that closely satisfy the given Euler's equation and exhibit the blow-up behavior. So this is one of the example where the neural network found a set of solution that had not been previously found with more classical methods. Because as you know, like if you want to resolve the singularity, you need really high resolution to capture the structure of the singularity. And here we are solving everything in a self-similar domain that avoid that problem. And we can add many mathematical knowledge that's known about the system, such as symmetry and smoothness. We can impose this directly in the cost function, so it adds a lot of flexibility. And this is very exciting for us. So Charles Pfefferman, he is a mathematician at Princeton, and he wrote the original statement of existence and smoothness of the Navier-Stokes equation. He's not directly involved in this work, but he mentioned in the Quantum Magazine that our solution is quantitative, is precise, and has a good chance of being made rigorous. So just to sum up, I talk about multi-stage neural network. It can boost approximation accuracy. It can represent multi-scale flows. We can apply it to multi-scale inverse problem that is constrained by partial differential equations. And if you're interested, our code is open source, so you can just download this, and then there's some simple examples I play with. We're trying to wrap up another paper that include do everything automatically, like such as selecting the frequency, etc. But with that, I'll end here and take questions.
Okay, so let's thank Dr. Lai for the great presentation. So I have one quick question. So have you tried to relate to the singularity problem? Have you tried to study first some simpler equation? For example, the supercritical nonlinear Schrödinger equation. So, for example, that type of equations, there are basically definitive results in most cases, theoretical results. So, in which the blow-up solution is perfectly described. You know exactly the rate of blow-up, at the finest possible detail. And so maybe those are good problems as a toy problem. Those are very hard papers when you propose this. Yeah.
Absolutely. You're talking about nonlinear Schrödinger. So I couldn't, which equation? Are you talking about nonlinear Schrödinger?
So nonlinear Schrödinger equations with L2 supercritical linearity, for example.
Yeah,
so those are solutions, those are problems, for example, focusing nonlinearity. So you admit standing waves. In some cases, when you have L2 critical, we have a clear profile representation of the blob solutions. And then you have large theory on also supercritical cases. And in those cases, you have a better understanding on how the solution blows up with respect to the Navier-Stokes equation. So even if those problems are still hard, there might be some sort of toy problems for the Navier-Stokes equation. Even because there is a fluid dynamics representation of those equations. And most recently, that representation has been taken advantage of for some theoretical results for concerns the even harder nonlinear Schrödinger equations for concerns the blow-up problems, namely the defocusing energy supercritical nonlinear Schrödinger equation. There was a conjecture which was having solution which was scattering, but actually this conjecture was proved differently by recent authors between Frank Mer, Pierre Raphael, many other people. But my question is related to simpler models that have a better, which people have a better theoretical understanding than Navier-Stokes, might be possibilities on which you can study this methodology, apply this methodology.
Absolutely. We were actively working on so we are not directly working with nonlinear Schrödinger equation right now, but we work with various set of simple equations that exhibit blow-up behaviors. And so I'll be actually very interested in the reference you mentioned about like the focusing of the energy. But so right now, I think the most challenging equation we have, the most challenging simple equation we find is the ones that has unstable solutions. Because those are the ones that we think is really difficult for the classical numerics to find. So for example, I guess the simplest one is the inviscid Burgers equation. We're trying to find the higher order smooth solution that is unstable. And so any system that exhibit smooth solution that blow up but also is unstable is definitely of interest. And nonlinear Schrödinger's equation is also on our list. Yeah.
Awesome. We have one more question, and yeah, for closing the seminar. Yes, please.
Yeah, can you hear me? Am I clear?
Maybe can you speak louder?
Yeah, come.
Yeah, is this better?
Yes.
Okay. So I've sort of been interested in like the fact that like a lot of black box algorithm, machine learning and neural networks are like really good for finding solutions, but are less useful when it comes to like discovering like dynamics or laws or things that we can really set in, like use as really solid. So I found it super interesting when you mentioned like using neural networks to sort of develop like counterexamples to maybe like establish principles. So if I'm understanding correctly, could like uninterpretable methods be used to create like counterexamples and disprove like theorems and stuff that have come from interpretable methods?
Yeah. I'm really glad you asked this question. Because I think the neural network is giving you hints, right? It's a tool, but eventually what you can do is dependent on who is using it, right? Like eventually, if you want to, I think there's still a substantial. So for the singularity project, for example, finding this highly accurate solution is really just the first step, and then there's still this second half of the work that's looking. So which is what my colleagues are working on. Tristan and Javi and Gonzalo. They're taking these solutions and they're trying to conduct computer-assisted proof. And when I talk to them, and they say that it's really useful to be able to see the shape of the solution to get some hints of what they need to do. That definitely, I would say there's a two-stage procedure. Finding solution is the first step, but you still need to create insight. And that part, so far I still haven't seen any machine like any algorithm that can do that part. I think that the proof part almost certainly is, in this problem at least, is human generated. So I would say the numerics helps, but that's definitely to generate the final insight. It's still our job, still the like the mathematician's job or scientist's job.
Yes,
Awesome.
thank you.
Awesome. So, well, thanks a lot for the great presentation, for your questions. It was a great pleasure to have you in the program. So thank you very much.
Thank you.
Just an update. So we're gonna have to move from the room. So we're gonna go to another room for the workshop.
Okay.
So
All right. Then I'll say,
bye.
yeah, thank you. Bye. See you. Have a good day.